Hello, this is Quincy HUHN presenting my project Accelerating Radiation Transport Solves with Artificial Neural Networks. Before I begin, I'd like to thank the OREU program organizers and sponsors for financing my summer internship, and my mentors John Ragusa and Mauricio Tano for their help and guidance. So, why radiation transport? Well, it's used to solve many different types of problems, including the transport of neutrons in a nuclear reactor, like the trigger reactor here at A&M, the transport of photons in radiation therapy, or even the heat transfer within stellar and planetary atmospheres. So basically, it's applicable wherever neutral particles are transporting within a medium. And there are some difficulties with solving radiation transport. Radiation transport is a 7-dimensional problem. That's 3 dimensions in space to an angle, 1 in both energy and time. And with just 100 discretizations in each dimension, that is already a trillion unknowns in steady state. And we don't have enough RAM to solve this entire system at once. So instead, we must use methods that solve a series of one-cell problems that we can solve one energy group, direction, time step, and spatial cell at a time. And the equation that we're then solving is the linear Boltzmann equation. And I have here the 1D monoenergetic steady-state version of that equation, so I can explain kind of what's going on. So the first term is the streaming, which determines the particles going in and out of the cell that you're concerned about. The reaction is basically the absorption and scattering within the cell that you care about. The scattering then is the particles that are scattered that come back into the cell, and the inhomogeneous source term is the particles that are born within the cell. So the general method of solving this problem is we assume a scalar flux and build this source term, and then that allows us to solve for the angular flux on the left-hand side, which we then use to compute the scalar flux and recalculate the source term, iterating on this until there's no change within the scalar flux and we have a converged system. This process is called source iteration. And so you can see that any small error within the angular flux solution will cause a buildup in error in the total scalar flux. And so how we solve this on the medium as a whole is the process called sweeping. So we take boundary conditions and material properties along with the inhomogeneous source and solve cells one at a time until all the cells in the medium are solved. The output flux becomes the input flux for the neighboring cells, and we can sweep along the medium, something like this animation. And so because we have to solve so many of these one-cell problems, any increase in speed on the cell level can greatly speed up the program overall. And so the way that we propose to speed up this program is by using sweep nets. So we use a vanilla artificial neural network architecture implemented in TensorFlow, and the sweep nets approximate the radiation transport solutions for one-cell problems using fewer operations than the assembly and solution of a one-cell system of equations. And this fact means that acceleration can be achieved with sweep nets by speeding up the individual cell solves. And so to go into a little bit more of specifics of our architecture, the solution to a radiation transport problem can be broken up into two parts: the transmission contribution, and the source contribution. For both the positive and negative directions, we have a neural net that solves the transmission contribution and the source contribution, which means altogether we have 4 neural nets that together form our ability to solve a radiation transport problem with our sweep nets. And so first to go over the transmission results. So our transmission neural net has 2 hidden layers of 2 neurons each, and there is a sigmoid activation function on all of the layers. And with this, we're able to get a very close match between the artificial neural network and the SN solution, which is the discrete ordinate solution, which is the general method of solving radiation transport problems. And so now that we have this transmission part solved, we can then move on to the source contribution portion. And again, this neural net has 2 hidden layers, but this time of 8 neurons each, and again, the sigmoid activation function on all of the layers. And the source contribution is more difficult to represent than the transmission solution due to a more complex relationship between the input and output for the source contribution. And again here, we're able to pretty closely reproduce the SN solution with our artificial neural network. And so once we've solved these very basic problems, we move on to a more benchmark type problem, which is Reed's problem. And so Reed's problem in general is used to benchmark SN solutions, and it's a difficult problem to solve because of the vastly different material properties that you're dealing with, as well as the scattering that exists on the right-hand side of the medium. So this scattering will cause many source iterations needed in order to fully converge the scalar flux, and this will cause a buildup in error. if we're not careful with our neural nets. So first, we tried to solve the pure absorber solution, and we're comparing here the artificial neural network to the SN solution, and we're able to pretty closely replicate this pure absorber solution. But in this case, we're not able, the vanilla neural network does not converge in the scattering case. So because of that, and the wide range of source values and cross-section values, led us to the implementation of a mixture of experts model. So our mixture of experts model, instead of having a single model be used for all of the different regions, we train multiple different ANNs, or experts, on different data sets to give us a picture of the whole data set as a whole. So the input will be fed into all of the networks, and then the gating network output will be combined with the output of each of the individual experts in order to form the total output of the mixture of experts model. This gating network will determine which expert will have the most accurate output and try to represent that more in the solution. And so the goal is kind of that each of the experts provides a good representation for the solution in different regions, and then overall the mixture of experts model is able to model the whole problem with a good representation. So first we needed to verify that our mixture of experts was implemented correctly. So we ran our model with only one expert and one gate, loading the weights from our vanilla artificial neural network solution to determine if our model was implemented correctly. And so here you see a slight discrepancy, and this loss of accuracy is due to the output of the gate asymptotically approaching 1, but it never is 1 due to the softmax function that determines the output of the gating function. But overall, this result shows that we correctly implemented our mixture of experts model and that we could now begin to optimize the training on it. And so for our results, we went with 7 experts and 1 gate because 7 was where we were able to gain the best results without going over and adding to the computational cost of each feed forward. And again, this is the pure absorber case, and our mixture of experts model is better able to approximate the SN solution than just the vanilla neural network. And then the mixture of experts model has the added benefit of being able to converge in the scattering case. So again, this is the same mixture of experts model, and here again, 7 experts in 1 gate. And so this is the scattering case. And this has to undergo the source iteration method that I've been describing, where the source is updated after every solve until it converges. And this result is really good because we are able to fully converge even through source iteration, where a small amount of error would build up over time and cause our solution not to converge. So the fact that we're able to closely approximate the SN solution with this neural net, even having to undergo source iteration, shows that this is a really, really strong and well-trained neural net. So for potential future applications of this work, you could apply a recurrent neural network architecture to sweep nets in order to improve their accuracy, or increase the dimensionality of the problem to 2D or 3D in space. So in conclusion, our artificial neural network was able to approximate the solution to the read problem in the pure absorber case, and then when we added the mixture of experts to our model, the scattering case of the read problem, in addition to the pure absorber case, were able to be solved very effectively. And so we are writing currently a journal paper summarizing this work due to the novel application of this mixture of experts to radiation transport. Thank you.